So I want to look at some examples where there's only two variables present, and these examples really serve as inspiration and motivation for a lot of what we're going to do. They really model how linear systems tend to work. And so I just wanted to point out the remark here. Finding the solution set for a system of two linear equations and two variables is relatively easy in the sense that you're just finding the intersection of two lines. Linear equations and two variables are just lines in two space. And so you should think of x1 playing the role of x and x2 playing the role of y, like we talked about earlier. So let's go ahead and graph these lines. We're gonna work this out graphically. There are ways that you can solve these systems non-graphically, but I don't care about that as much just yet. So graphically, if we were to graph the first equation, we could think of it as x plus y equals 3 and x minus y equals minus 1. So for the first equation, I say, okay, when x is 0, y is 3, so we'll put a line there. And then when y is 0, x is 3, so we'll put a line there. And we've got the first line. There it is. Hopefully we can get it to go through my dots. There we go. There it is. Second line, let's think about it. When x is 0, y is, well, minus y is minus 1, so y is 1. Let's graph that one in blue. So y is 1. And then when y is 0, x is negative 1. And so there's that line. And so we can graph these. And, whoop, that did not quite work out. Let me try again. It's kind of hard to get my line to go straight. Something like that is good enough. Okay. So there it is. Here's the other line. And you can actually visually see the solution right there. There it is. Let's maybe use a different color. So there is the solution. And the solution set is, there's only one point in the solution. This thing has one solution, and it looks like it's when x is 1 and y is 2. And there's a unique solution. There's only one solution. So even though there are two numbers involved in your solution, there's one solution. This pair of numbers is a solution to this linear system. Okay, unique solution. All right, next equation. So let's go ahead. Whoops, next system. Let me close this. Okay, so we'll just graph the first line. So x2 plus x1 is 3. That's saying y plus x is 3. We actually just graphed that one before. X when x is 0, y is 3. When y is 0, x is 3. We've got that one. No problem. Oops. There's a problem because I can't seem to graph it. There we go. Close enough. Okay, so there's that one. Now when we go to graph the second one, let's maybe do red. We say, okay, the second equation is 2x plus 2y equals 6. Well, when you simplify, you're back to x plus y equals 3, which is the same line. And so those are two different equations. And when I graph both equations, I realize that these are the same line. And so they intersect at infinitely many points. Here, there are infinitely many solutions. And any point on this line is a solution. So there's a solution, and there's a solution, and there's a solution, and there's a solution, right? There's infinitely many solutions. So the solution set to this system is actually all points living on that line. All right. So there we go. So we have first example, there's a unique solution to our linear system. Second example, that's really sloppy. Let's see if we can rewrite that. Second example, there's infinitely many solutions. And then finally, our third example, let's go ahead and keep graphing. So the first line you should recognize by now, right? X plus y equals 3. So we're just going to go 1, and then there we go, and something like this. Okay, so there's the first line. Second line, x plus y equals 1. So then we're going to go something like that, and boom. And I'm going to try to slide this thing. Now, there we go. Okay. Sorry, graphing digitally here is not always easy. So these lines are not hard to check. You can see it visually. These lines are parallel, so parallel lines. And so what does that mean as far as finding a solution set? Well, they have no solution. So let's go back to the beginning of this. And what do we say? The solution set to a system of two linear equations in two variables, it's just the points of intersection of the two lines. And so here there was a unique intersection. There's only one solution. Here these lines intersect at every single point on either one of them, right? So there's infinitely many solutions. Here the lines never intersect, and so there's actually no solution. And so it turns out that what happens in the two-dimensional case actually describes every case. And so I want to look at a theorem with you, and then we'll end this video. So every system of linear equations, and I'm going to actually write a little something. This is in any number of equations, any number of variables. Right? When I say every system of linear equation, every system of linear equations, I really do mean every. It has precisely one of the following three options as its solution set. So one option is there's simply no solution, period, end of story. The second option is there is a unique solution. What does that mean? I.e., there's exactly one solution. And three, you can have infinitely many solutions. Okay? And so going back, let's scroll back up in the notes for a minute. We talked about a linear system is called consistent if it has at least one solution, and inconsistent if it has no solutions. And so now we realize that, okay, the no solution situation, this is inconsistent because there's no solution. A unique solution means you do have one solution, and so in this case, the system is considered consistent. And even having infinitely many solutions means you have at least one solution, and so you're still considered consistent. And so really, what we want to think about before we end the video is, what are some kinds of solution sets that can't happen? So why don't you pause the video, think about that for just a second. So you can't have, let's say, 3 solutions or 5 solutions, or when I say 3, I mean exactly 3. I can't have exactly 3. Yeah, I should rewrite that, because if you have infinitely many, then you have 3, but you have more than 3. Can't have exactly 3 solutions, 4 solutions, even 2 solutions, right? Etc. I won't write this, but you can't even have countably many solutions. So when I say countably many, I mean like infinitely many, but 1, 2, 3, 4. There's actually uncountably many solutions. If you don't know what that means, don't worry about it one bit. For those of you that remember discrete or have seen some analysis or something like that, you'll know the difference. So anyway, you can't have exactly 3, 4, 2, 10, right? You either have none, 1, or infinitely many, and actually uncountably infinitely many. All right, so let's end this video here, and then we'll go on.